Good morning, students. Welcome back to experimental stress analysis classes. That is Module 3 and Class 3. In this session, we will be discussing about the effect of how the stressed model in a plane polariscope will be taking place. In the previous classes, we have discussed about what is polariscopes and what are the different types of polariscope and how the model behaves under this polariscope. In continuation with the previous class, today we shall discuss about the effect of a stressed model in a plane polariscope, that is dark field setup. Now let us consider a plane stressed model inserted into the field of a plane polariscope with its normal coincident with the axis of the polariscope. Okay, note that the principal stress directions as the point under consideration is the model makes a very important role. That is, the angle of the incident of the axis of the polarization is very important. Here in this figure you can observe the model which is being stressed is placed between the polarizer and the analyzer. Now when a ray of light which is passing from the source and which is being passed over the polarizing axis, and here the polarizer allows the normal direction, whatever the plane, whatever the rays which are passing, it should be only parallel to the polarizer axis, then only it allows further the rays to pass. Now here in the figure you can observe that the plane polarizer resolves an incident light wave into two components which vibrate parallel and perpendicular to the axis of the polarizer. The component of the parallel of the axis is transmitted and the component which is perpendicular to the axis is instantly observed. Since the initial phase of the wave is not important in this development of the fringes, we will be neglected. Now you can observe the first one where the analyzer A, which is kept only for the, we will take it as the axis of the analyzer as A0, and the model we will be taking it as M. Consider the model symbol as M, and the axis which is following, whatever the rays that are following, will be taking into two vibratory angles, that is AX, that is a fast moving axis, and slow moving axis. And the model on the end one we will be placing a polarizer, and polarizer always it will be placed in perpendicular to the analyzer. Now in this one, the linear polarizer which is nearest to the light source is called as polarizing light, or the polarizing or transmits the polarizer, and of course it transmits the plane polarized light into the axis. Second one, the linear polarizer which is far away from the light source called as analyzer, and which will allows the rays which are passing from the model to the what you call as view, or whatever they through the analyzer, only which is passing in the horizontal directions. Now the model, let us insert the model, and which is to be viewed by an analyzer. The polarizer is kept perpendicular to the axis of the light. These are the points to be remember. The polarizer is kept perpendicular to the axis of the propagation, which transmits the light wave which comes from only from the three axes. The analyzer which is kept at 90 degrees or perpendicular to the polarizer, and it transmits the light, and the light components will be whatever the light component which is vector transmitted to the polarizer, which is given by the light vector, which when incident on the model is resolved into two components, that is along the axis of which is parallel to the plane of the analyzer and perpendicular to the plane of the analyzer. Now by considering this one, we will move further with the effect of stressed model in circular polariscope. In circular polariscope, there are two possible arrangements for a circular polariscope, that is polariscope setup. In the first case, whatever the quarter wave plates, here two quarter wave plates are mounted, whatever the quarter wave plates are kept crossed, it is fast axis of the quarter wave plate is parallel to the slow axis of the quarter wave plate. And along with this one, the polarizer and analyzer are kept crossed, and light is emitted from the source S. The unpolarized light becomes plane polarized, right, after passing through the polarizer. After passing to the polarizer, that will be polarized. And plane polarized light is made to pass through the quarter wave plate, which is converted into a circularly polarized light. Now, in this model, a circularly polarized light is placed into the model, which is a crystal material, and double refracting phenomenon occurs with remaining to the phenomenon of the refracting rays. Now, in this one, the circularly polarized light is converted into a plane polarized light after being passed through the second quarter wave plate, and which is kept crossed to the first quarter wave plate. You can observe the second quarter wave plate is placed with respect to the first quarter wave plate, which employs a circular, the total dark field arrangement which employs a circularly polarized light. And the first element of the light source is called as a polarizer element, and which converts the ordinary light into a polarized light. And the second wave, that is a quarter wave plate, which is mounted at an angle of 180 by 4, that is 45 degrees to the plane of polarization. The second quarter wave plate converts a circularly polarized light into a plane polarized light. See here, look into the sketch carefully. Here, the intensity of light coming out of the analyzer is 0, as it is kept crossed with respect to the polarizer. Thus, due to the zero intensity of sources, due to the zero intensity of the sensor, and the dark field will be appearing on the screen. Whereas in the second case, the two quarter wave plates are parallel to each other. If it is a second case, two quarter wave, first quarter wave plate and second quarter wave plate are parallel. In this condition, you can observe two quarter wave plates are parallel to each other at an angle of which act as a half wave plate, and the incident, which is a linearly polarized light, gets rotated by 90 degrees. Therefore, the light waves will not be having any effect on the analyzer. Hence, the intensity of light entering the screen will be 0, which is separated by the series of dark bands. Now here, look into the sketch here carefully, which shows the arrangement of the circular polariscope with the dark field arrangement. In the second case, as I indicated, the polarizing and analyzers are kept parallel to each other. That is what the lambda by 4 or quarter wave plates are kept crossed. Therefore, the unpolarized light becomes polarized light after placing through the polarizer, which is converted into a circularly polarized light after going through the first quarter wave plate circularly. Now, which is converted, whatever the polarized light which is being converted into a plane, which will be converted into plane polarized light after passing through the second quarter wave plate, as it is kept to the crossed with respect to the first quarter wave plate. This is about the same thing which I explained here. The first element of the modeling, which converts ordinary light into plane polarized light, and the second wave plate, which is a quarter wave plate, which is about an angle of 5 by 4 to the plane of the polarization. The second quarter wave plate, which converts circularly polarized light into a plane polarized light. Now, the second bit is production of fringes. How we do necessary of production of the fringes? The See, the fringes, whatever the rays which are falling, which will be falling from the stressed model, can be observed in terms of the fringes. So we can determine the fringe order to the nearest half order of the by using the dark field arrangement as well as the light field arrangement. Now, the photoelastic materials, which are constructed from a special class of transmit material which exhibit the property known as bifringence. These bifringent materials can be studied by using certain techniques and which have ability to split an incident plane polarized light into two components. Now, the fringe order determination for the fringe production, whatever the production of fringe orders, when we need to there is a necessary for the fringe order determination. We can determine the isochromatic fringe order to the nearest half order of the using both the dark field arrangement as well as the light field arrangement of the polariscope. Further improvement on the accuracy of the fringe order determination. Here we can even achieve either by using a mixed field pattern or by fringe multiplication methods. Therefore, in order to achieve higher accuracy as it is desirable in many applications, the following these methods can be amplified. Which are these methods? Those methods are nothing but the Babin and Solel compensator and 3D method. See, many other conventional methods for determining these fractions of fringe orders are determined, but only the major things are nothing but the Babin soil compensator and 3D methods are very important. Now, the compensating methods compared to this one, the first one, the Babin soil compensator. So you can observe this one, the Babin soil compensator, which includes the compensator of a two crossed wedges. This is the two crossed wedges which can be mounted, which is be having A and B. This is A and the other one is placed here. A and B, that is called as the two components, that is a wedges A and B, which are cut similarly with their optical axis. Now, in this one, the fast axis of both the wedges are similarly oriented. The fast axis of both the wedges are similarly oriented because they form if we have the same orientation, they form one rectangular piece of uniform thickness. And here let us consider the material for this one, the quartz material, the quartz plate of uniform thickness T, of a uniform thickness whose fast axis is at right angle to the fast axis of the wedge fast axis of the wedge construction. Now, in this method, the relative path of the as a relation between the plate C, which has been cancelled partially by the varying of the thickness of the wedge, can be determined very easily. Now, by adjusting the overall thickness of the wedge combination, the components of the added substitution can be very easily arranged. See, there is a micrometer screw. You can observe at the top one, there is a micrometer screw which is calibrated in terms of number of wavelength which can be added or subtracted along the imaginary axis. See, the compensator which has been kept before and after of the model is oriented along the principal axis, or the principal axis in the sense the principal stress axis of the model. See, from the zero position, the micrometer head is turned either on the either side until the dark field fringes can be obtained. Now here you can, of course, what I told, the instrument consists of a quarter wave plate of uniform thickness T1, where A and B are the two quads together, that is a quad wedges together, which form a rectangular piece of uniform thickness. Because this material should be of uniform thickness, which should not be varied at any cost. See, that optical axis of the quarter wave plate and the wedges are mutually orthogonal. See, the quad is the permanently bifringent material. For that reason, we will be selecting such kind of elements. See, the bifringence exhibited by the compensator can be controlled by moving the wedge with respect to the others. The two wedges which will be moving with respect to each other. Now, the fast axis of the quarter wave plate is at right angle to the fast axis to the wedges A and B. Now, the retardation given by the plate can be cancelled partially or fully by varying the thickness of the wedge combination. Yes, of course. Say only by varying the what you call as the quarter wave plate has the ability to cancel all the partial waves, and that also depends upon the thickness of the wedge and combinations. The retardation is zero when the thickness is when the two what you call as plate thickness are equal. Suppose when any of the thickness, if the second thickness of the is greater than the first what you call as wave plate, then the negative, we'll call it as a negative fringes we can be obtained. Therefore, the resultant retardation produced by the instrument depends upon the thickness of the greater wave plate. That is a greater wave or the plate that is called as wedges, either T1 or T2. Now, in general, the working conditions select a particular point in the model where the fringe order is to be determined. Now, this order has to be placed such that whatever the model that has to be placed in accurate, such that the point should be very clearly visible by the analyzer. Then the isoclinic are obtained at a point of intersect to determine the direction of principal stresses using the plane polariscope. These compensator, whatever the compensator which are kept before and after the model and is oriented along the principal axis are kept by adjusting the screw micrometer in proportional to the fringe order and selected points. See here, only by adjusting the micrometer proportional, we can observe the fringe order, whatever which can be observed by the analyzer at the end, that is the end element of the polariscope. This is about the first method, what we call it as a Bevbent Solel construction, and this is also which is called as a fast axis and slow axis movement. The next one is the trade method of compensation. See, this method, whatever the elements used in this circular what you call as polariscope itself consists the arrangement of the trade methods. See, already we have discussed the same thing in terms of a circular polariscope. The same elements are being used in this method, or this method can be implemented to determine for the circular polariscope. Now here, the light source, whatever the light source which will be considered here, the light source S emits a unpolarized light which is made to pass through the polarizer P. The working principle I am telling you here, the elements which include the source, the polarizing element, the first quarter wave plate, the stressed element, this is the stressed element, and the second water wave plate, and the last one is the analyzer. The analyzer, whatever the analyzing plate, is always kept at an angle of 45 degrees compared to the what you call as polarizer here. So this arrangement which includes the light source S, which emits the unpolarized light which is made to pass through the polarizer P. After emerging out from the polarizer, the polarized light is made to fall on the what you call as angle at an angle of 45 degrees to the axis to the first quarter wave plate, which is circularly polarized, and will be emerging out as if the first quarter wave plate is having two vibratory two vibratory endpoints along the the fast axis and slow axis with respect to the with respect to the first quarter wave plate, and which can be considered as the separation methods. Now here the method, of course, the method is generally preferred for the bandwidth Solin methods. Since no auxiliary equipment is required, and analyzers polariscopes are aligned with the direction of the principal stresses. All other components of polariscope rotated relative to the polarizer, and the standard dark field polariscopes exist. Now observe here the arrangement of the including the analyzers, the two analyzer, one polarizer, and the quarter wave plates can be oriented by an angle at 45 degrees with respect to each other. Now the two vibrating components along the fast axis and slow axis are respectively represented as the fast axis and represented as A3 of, that is a fast along the analyzer. I can take it as A3L is equal to minus A by root 2 of sine omega t minus pi by 4 plus delta, and into cos of minus pi by 4 plus A by root t into cos omega t minus pi by 4 into sine minus pi by 4. On further reducing this equation, we can rearrange or we can rewrite it as minus A by 2 into sine of omega t minus pi by 4 plus delta minus of A by 2 cos of omega t minus pi by 4. Similarly, for the second quarter wave plate, we can even write it as A4 as the light. So that is A4 is equal to minus A by root 2 into sine omega t minus pi by 4 into cos of minus pi by 4 plus A by root 2 into cos omega t minus pi by 4 plus delta into sine minus pi by 4. And this can be even rearranged by considering the sine omega elements. So here the above equation can be reduced as, that is minus A by 2 into sine omega t minus pi by 4 minus A by 2 into cos omega t minus pi by 4 plus delta. Now in the above equation, let gamma be the angle through which the analyzer should be rotated to obtain the extension, that is AAX is equal to 0. Then AT, that is considering on the thickness plate, AT is equal to A3L into cos pi by 4 plus gamma minus A4L into cos pi by 4 minus gamma. Or we can even rearrange this one as AT is equal to A sine omega t plus delta by 2 into sine delta by 2 minus gamma. Now if the intensity of light is 0, suppose if the intensity of the light is 0, then the sign can be taken, the equation can be reduced to sine of delta by 2 minus gamma, that is equal to 0. Or even it can be written, I'll take the sign on either side. I'll be taking the delta by 2 minus gamma is equal to m into mu, m into pi, or delta by 2 is equal to m pi plus gamma, where m is equal to 0, 1, 2, 3 and so on. And n is nothing but here delta by 2 pi, that is equal to m plus gamma by pi. Now if the analyzer is rotated in the opposite direction, then n is equal to delta by 2 pi, that is equal to m plus 1 minus gamma by pi. Now in this arrangement, a plane polariscope is first employed as an isoclinic, or they are called as a fringe, which will pass through the point of interest. Finally, a plane polariscope is converted into a circular polariscope using the dark field arrangement. Then the analyzer is rotated until the execution occurs. Whatever the fringes can be occurred, that can be occurred only by rotation of the analyzer, which occurs at a point of intercept. This is about the 3D's method of compensation. In the second one, the 3D's method which can be observed, and here the elements which are used in the 3D arrangement, the elements which are used in all the elements used in the circular polariscope, same elements which are used in the circular, which consist of the arrangement of the 3D method and the compensation. See, the light source S emits of the polariscope. Now the arrangement, what are the steps we need to decide for the arrangement of the Freddy's method? Here in this Freddy's method, the method is similar to the 3D's method as compared to the as compared with respect with as compared to the 3D's compensated, except only by the first quarter wave plate. Here in this method, which uses only the one quarter wave plate, a polarizer, after the polarizer a stressed model, then the quarter wave plate, and finally the analyzers. Now this method, whatever in this method, the purpose of using the first quarter wave plate is to produce only a circularly polarized probe, which include, well, that is when it enters into the stressed model, which will give an equal amplitude along first reticulus normal stresses, that is sigma 1 and sigma 2 axis of the model. Since the axis of the second quarter wave plate, which is kept at a now here, which is kept at 45 degrees to the what you call as principal stress axis, so addition or subtraction of the quarter wave plates will always produce a linearly polarized light. In the present method, polarizer is kept oriented at an angle of 45 degrees to the principal stress axis, that is sigma 1 and sigma 2 axis of the model, without the first quarter wave plate. Now here, the steps which are necessary to determine the Freddy's method, that is how the rays can be prepared, that is the first step. Remove the first quarter wave. Since there is no any first quarter wave plate, we have been removed the first quarter wave plate. The second quarter wave plate, which is that is a which is now the second is that rotate the polarizer and analyzer so that their axis makes an angle of 45 degrees with the principal axis. The principal axis, the axis will be kept along a 45 degrees with respect to the principal axis. Now third, principal axis direction to the model at that point of interest. Next one, third point, rotate the second quarter wave plate until the axis is parallel to the axis of the polarizer. Whatever the second quarter wave plate will be considering, this should be rotated until the the axis is coinciding with the polarizer axis. Then the light vector emerging out from the polarizer can be taken as A is equal to A cos omega t. And since the polarizer is set at 45 degrees axis to the principal direction in the model, then we can, the light entering the model of the vector is resolved into two components, that is A1e is equal to A cos 45, and A1e either I can reduce to as A cos omega t of A omega t 1 by root 2, and A2 similarly A2e is equal to A cos 45, that also I can rewrite it as A2e is equal to A cos omega t, that is into 1 by root 2. Then the model introduces a phase difference of, on leaving the model, then the components of light vector which is coming out from the polarizer can be taken as A31 A1L as A cos omega t plus delta t into A by root 2, or I can rewrite it as A2L is equal to cos omega t into A by root t. Then the first axis of the quarter wave plate is set at 90 degrees to the polarizer axis. Hence, on entering the quarter wave plate, the light components become E is equal to A1L cos 45 minus A2L into cos 45. Or we can even rewrite it as AE is equal to A by 2 cos of omega t plus delta minus cos omega t. And similarly, for the second quarter wave plate, if we are mounted, that is AB is equal to A1 of cos 45 plus A21 of cos 45. Or even you can rearrange that the light waves which are receiving, that I can write it as ABE is equal to A by 2 cos of omega t plus delta plus cos omega 2. Next point is that whenever the light source which is leaving from the quarter wave plate to the quarter wave plate is introduced, the phase difference of 5 by 2. Hence, on leaving the quarter wave plate, the light vector becomes A1E is equal to A by 2 cos of omega t plus delta plus pi by 2 minus of cos of omega t plus pi by 2. Or I can write it as AT is equal to A by 2 minus sine of omega t plus delta plus sine omega t. Similarly, for the second quarter wave plate, I can write it as ABL is equal to A by 2 cos of omega t plus delta plus cos omega t. Next one is that the analyzer is rotated at an angle of gamma to obtain the extension at a point of interest. Then the light transmitted through the analyzer can be written as AT is equal to AT cos gamma minus ABI of sin gamma. Or I can even read it as AT is equal to minus A by 2 sin omega t plus delta minus sin omega of cos gamma minus A by 2 cos of omega t plus delta plus cos omega t into sin gamma. Or further, this above equation can be reduced to AT is equal to minus A by 2 of 2 cos omega t plus delta by 2 into sin delta by 2 cos gamma plus 2 cos omega t plus delta by 2 into cos delta by 2 sin gamma. Now, when the intensity of light is 0, that is intensity I is equal to A square of sin delta by 2 cos gamma plus cos delta by 2 sin gamma whole square, that is equal to 0. Or when I remove the brackets, sin delta by 2 into cos gamma plus cos delta by 2 sin gamma is equal to 0. Therefore, sin of delta by 2 plus gamma is equal to 0. This is about the Faraday's, that is a Fredel method of what you call as stress compensations. Next one, the fringe multiplication techniques. How do we multiply the necessary things of the fringe multiplication? That depends upon the mounting of the quarter wave plates. In this extension meter, we will be considering the fringe multiplication, that is a practical mirrors, how the fringes can be increased, which can be observed, so that which will be helpful in observing very clearly. So here in the of course, the compensation technique, where the fractional orders of the fringe can be determined simultaneously at all points on the model, and partial mirror can be used to multiply the number of isochromatic fringes, because the partial mirrors which will be implemented, which is kept across both in a cross manner, this will be helpful in what you call as refracting the light sources. So the final wave which will be in representation of the isochromatic fringes. Now, if one partial mirror is placed parallel to the photoelastic model and the other partial mirror is placed slightly inclined with the plane of photoelastic model, then you can observe by the calibration techniques. So here the calibration techniques which can be implemented by an example, we will be considering it as a bar which is being applied by a tensile force in either directions. So under load, the uniform stress in the test specimen is sigma 1 minus sigma 2, that is equal to P by WH. Or we can even read it as the applying stress optic law, we get it as sigma 1 minus sigma 2 is equal to N into sigma F by H. In this method, where load P has to be adjusted to have a full fringe order in the field of view. Now, in the other technique, the trendy method of compensation used where for a particular load P, the extension angle are plotted against the applied stress. Then by knowing the slope of the curve, we have sigma f is equal to sigma 1 by gamma into h, into which is been at an angle of 180 degrees. Now, in this method, the beam, whatever the consideration of the extension meter, which is being plotted against the applied stress. Then by knowing the slope of the curve, we have sigma f is equal to sigma 1 by gamma into h of 180 degrees. And the second method is beam under bending. So the beams which are subjected, that is a photoelastic material of the beam, which are subjected by an external loading, and because of this load thickness, the fringes which will be obtained on either on the plane polariscope can be observed very clearly. For this one, a rectangular beam of thickness h at a depth of w may be used, and which is subjected to pure bending. That is what to determine the pure bending in the beam, which can be considered by applying the load P at a distance and from the bending moment, and the bending moment in the middle portion of the beam can be taken as M is equal to P into A. The stress in the beam R sigma is equal to M by I into Y, or where bending moment M can be written as M is equal to P into A divided by a moment of inertia for that bending moment, that is a simply supported hw cube by 12 whole square into that is w by 2, or we can reduce that as pa divided by hw square by 6 into sigma 2. That is what the sigma 2, whatever they do for the plane stresses, sigma 1, and since sigma 2 is 0, which will be considering in only one plane. Thank you. So this is about what are the different methods which can be used for determination of isochromatic fringe pattern. In the next class, we'll be considering and to determine how the 2D photoelastic materials and 2D elastic techniques can be used. Along with this one, we will determine what are the two different what you call as methods to determine that for a analysis of two-dimensional photoelasticity. Thank you.